All right, let's jump right in. Today, we're going deep, deep down into the world of computers.
Which is perfect because I think a lot of people use computers every day, but don't really have any idea what's going on in there.
It really is a hidden world, isn't it?
Yeah, kind of like a magic trick. But hopefully by the end of this deep dive, we can make it a little less mysterious.
I'm all for that. So, where should we even start? I mean, when we say computer, what are we even talking about these days? It's not just those big clunky desktops in a dusty old office anymore.
Definitely not. I mean, think about it. Your phone, total computer.
True.
Your car, computer.
Oh, yeah.
Probably even your refrigerator at this point.
Yeah, it's kind of wild how computers are, like, everywhere.
They really are everywhere. But even with all that variety, deep down, they all share the same basic DNA. They're all about input, process, output.
Okay, so break that down for me. What does input, process, output actually mean when we're talking about a computer?
Well, it's actually pretty straightforward. A computer takes in some information, that's the input, then it does something to that information based on a set of instructions, that's the processing part, and then finally gives you back a result, which is the output.
Okay, so like when I type a message on my phone, me hitting the keys is the input. Then the phone's software figures out what I'm doing, and then the letters popping up on the screen is the output.
Perfect example. And that same basic framework, that input, process, output flow, underpins everything computers do, whether it's something relatively simple like sending a text message or something incredibly complex like simulating the entire universe.
Wow. Okay, so it's all about the processing then. That's where the real magic happens.
You got it. And at the heart of all that processing power is the CPU, or central processing unit.
A CPU. Now, that's something I've definitely heard of.
It's often called the brain of the computer because it's the part that actually executes instructions, crunches numbers, makes decisions, all that good stuff.
So, like the brains of the operation. But what's actually going on inside that little chip, it can't just be a tiny brain in there, can it?
Well, not a brain in the traditional sense, but it's pretty amazing nonetheless. We're talking billions, with a B, of tiny electrical switches called transistors, and they're all packed onto a surface smaller than your fingernail.
Billions. Seriously, they must be absolutely microscopic.
They are, and every single one of those transistors can switch between on and off states millions or even billions of times per second.
Wow, okay, I'm trying to picture that, and it's making my head spin a little.
It is pretty mind-boggling when you think about it. But those on and off states, that's how computers represent information. It's a system called binary code ones and zeros, on or off, true or false.
Okay, so it's like a language based entirely on whether a switch is flipped on or off.
Exactly. It seems simple on the surface, but it's incredibly powerful.
So these transistors are doing all this super fast switching, but doesn't all that activity generate a ton of heat?
You're right, it does. That's why computers have fans and things like heat sinks. Those components help dissipate all that heat so the CPU doesn't overheat and burn itself out.
It's interesting how even at a microscopic level, we see these parallels to the way our own bodies work.
It's true. And just like our brains, the CPU needs a little help to do all those amazing things. It relies on what we call computer memory, specifically RAM and ROM.
Ah, yes, RAM and ROM. Those are definitely terms I've heard thrown around. Though I have to admit, I'm never quite sure which one is which. Could you refresh my memory?
Of course. Think of RAM, which stands for Random Access Memory, as your computer's short-term memory.
Short-term memory.
Yeah, okay. Yeah. It's basically the CPU's workspace, the scratch pad it uses to store data that it's actively working on.
So when I open a program or a file, it gets loaded into RAM so the CPU can quickly access it.
That's exactly it. But RAM is what we call volatile, meaning that as soon as you power off your computer, poof, everything in RAM just disappears.
Like wiping a whiteboard clean.
Exactly. Now, on the other hand, we have ROM, which stands for read-only memory. That's more like your computer's long-term memory. It's where those essential instructions that tell your computer how to basically turn itself on are stored. And importantly, ROM is non-volatile, meaning those instructions stick around even when the computer is turned off.
Okay, so it sounds like both RAM and ROM are super important for a computer to function properly, even though they do very different things.
Absolutely. They're both critical parts of what makes a computer a computer.
This is all starting to make so much more sense. We've got the CPU, the brain, doing the heavy lifting with its billions of transistors, and RAM and ROM acting like the short-term and long-term memory, helping the CPU manage all that information. But you mentioned transistors earlier, and I remember you saying that those aren't just found in CPUs, right?
Oh, you're right. We kind of went down a rabbit hole there.
No worries. It's all fascinating stuff.
But yeah, transistors are everywhere. Serially, they're in almost all modern electronics. They're like the unsung heroes of the digital age, quietly working away behind the scenes.
Okay, that's what I thought I remembered you saying. So we really do have those tiny little transistors to thank for basically everything. Smartphones, laptops, cars, even things like coffee makers. If it has a digital component, chances are there are transistors lurking somewhere inside.
You got it. And, for such a ubiquitous piece of technology, how they work is actually pretty straightforward.
Okay, so how do they work? What makes them so special? Give me the download.
So at their core, transistors are essentially tiny electrically controlled gates. They can either block or allow the flow of electricity.
So it's like a tiny little drawbridge that can be raised or lowered to either block or allow traffic to pass.
That's a great analogy.
Thanks. So when the drawbridge is down, the current flows. That's like an on state. And when the drawbridge is up, that blocks the current. That's an off state.
Exactly. And the really cool thing about transistors is that we can use other electrical signals to control that drawbridge, to flip it between those on and off states.
That's pretty wild.
Yeah.
But how do we go from a simple on or off to the complexity of a CPU that can perform billions of calculations per second?
Well, that is the real magic, isn't it? That's where things get extra interesting. To make a CPU, we need to connect lots of transistors together in specific ways to form what are called logic gates.
Logic gates. Okay, now you've really piqued my interest. What are logic gates?
Imagine you have a door, but this door has two locks on it, and the only way to unlock this door is to use two specific keys at the same time, one for each lock.
Okay, so it's like a super secure door.
Exactly. So you need both keys present at the same time to get that door open. That's essentially what a logic gate does, except instead of keys, it uses electrical signals as inputs. And instead of opening a door, the output is a change in the electrical signal.
So these logic gates are like the decision makers within the CPU, right? They're saying, okay, if this condition is met and this other condition is met, then I'll send a signal that triggers some other action.
You got it. Spot on. And by combining these simple logic gates in different ways, kind of like using different Lego bricks, we can create incredibly complex circuits.
So it's all about combining those simple logic gates in increasingly creative and elaborate ways to achieve more and more sophisticated tasks.
Precisely. It really is a testament to human ingenuity, isn't it? I mean, who would have thought that by cleverly arranging billions of microscopic switches, we could create machines capable of everything from simulating the human brain to, helping us order pizza with a few taps on our phones.
It's amazing when you think about it like that. And it's a great place for us to
Take a break.
Yeah. I need to let all this new knowledge sink in for a minute. But don't worry, listeners. We'll be back in just a bit to dig even deeper into the world of logic gates and uncover the secrets behind how computers actually think. All right, so before the break, we were talking about logic gates, which, as I understand it, are these essential building blocks for, like, all digital circuits. But you said there were only a few basic types.
Yeah, that's the really wild part. At the most fundamental level, there are only three that we really need to worry about. AND, or R, and NOT.
And, or, and not. Sounds like the start of a bad joke. Okay, but seriously, how do these three little words translate into the incredible things computers can do?
Think of them like primary colors. You can combine those few colors in different ways to create any shade imaginable, right?
Yeah, that makes sense.
It's the same with logic gates. You can combine these three basic gates in countless ways to build incredibly complex circuits that can perform all sorts of tasks.
Okay, so tell me more about these, like logic VIPs, AND, or R, and not. How do they actually work?
Okay, so let's start with the AND gate, since it's probably the easiest to grasp. Imagine you have two light switches that are wired to control a single light bulb. The light bulb will only turn on if both switches are flipped on, right?
Right. So you need both switch A and switch B to be on for the light to turn on.
Exactly. That's the AND gate in a nutshell. It requires both inputs to be true in order to produce a true output.
Okay, so using our light switch example, both switches being flipped on will be like a true input, and the light bulb actually turning on would be the true output.
You got it. Now think about how this plays out in a real computer. Let's say you've got a security system that requires a password and a fingerprint scan to grant you access.
Okay, two-factor authentication, super secure.
Exactly. Both conditions, the correct password and the correct fingerprint, need to be met before the system will unlock. That's the AND gate in action, making sure both conditions are true before giving the green light.
Okay, I think I'm getting the hang of this. So what about the OR gate? How's that one different?
All right, let's stick with our trusty light switch example. This time, imagine that the light bulb is wired so that it turns on if either switch is flipped on or if both are on.
Okay, so it's a bit more forgiving. Either switch on its own will do the trick.
Yep, that's the OR gate. It's all about options. As long as at least one of the inputs is true, you'll get a true output.
Okay, that makes sense. So if the A&D gate is like a super secure door with 2 locks, the OR gate is like a regular door where you can use either key A or key B to unlock it.
I like that. Another good example is a vending machine. You can pay with cash or our credit card. Either input will get you your snack.
I'm loving these real-world examples.
Okay.
So we got A&D, the stickler for the rules, and OR, the more flexible friend. What about NAUTI? What's its claim to fame?
The not T gate. It's the rebel of the group. Instead of combining inputs, it just takes one input and flips it. If the input is true, the not T gate outputs false and vice versa.
Like a logic flip switcher. Just takes what you give it and spits out the opposite.
Precisely. Think of it like a reverse button on a remote control. It takes the current direction, let's say play, and flips it to the opposite, rewind. Or how about this? Let's say you're writing a program and you want to perform a certain action only if a specific condition is not met.
Okay, so like if the user has not entered their password correctly, then display an error message.
Perfect example. The NOT gate is essential for situations where you want something to happen only in the absence of a particular condition.
This is all starting to make so much more sense now. We've got AND, OR, and NOT, 3 simple logic gates that can be combined in countless ways to create complex decision-making circuits. It's like we're uncovering the secret language of computers.
That's a great way to put it, but how do we actually keep track of all these different combinations of inputs and outputs? It seems like it would get pretty complicated pretty quickly.
Yeah, especially when you're talking about billions of transistors and countless logic gates all working together.
You're telling me that's where something called a truth table comes in handy.
A truth table. Intrigue me. Tell me more.
Basically, it's like a cheat sheet that shows you all the possible input combinations for a given logic gate or circuit and what the output will be for each combination.
So if I'm picturing this correctly, a truth table for an AND gate would show that the only time you get a true output is when both inputs are also true.
Exactly. For all other combinations of inputs, like if one is true and the other is false, or if both are false, the output will always be false. The truth table lays it all out in a nice, organized way.
So truth tables are like roadmaps for understanding how logic gates and circuits behave under different conditions.
I like that analogy. They're essential tools for designing, analyzing, and troubleshooting complex digital circuits.
This is also fascinating. We've gone from billions of tiny transistors flipping on and off to these simple logic gates making decisions to truth tables mapping out all the possible outcomes. It's like we're slowly but surely decoding the very language of computers.
And you know what? What's even more amazing is that this system, as complex as it might seem, is really just based on the simple flow of electricity.
It's mind-blowing when you really stop and think about it. We've built these incredibly powerful machines that have revolutionized our world, and it all boils down to harnessing the power of tiny particles moving through circuits.
It makes you wonder what else we might be able to achieve as our understanding of these fundamental forces of nature continues to grow.
Now you're speaking my language. But unfortunately, that's all the time we have for today's deep dive.
Oh, already. We didn't even get to talk about.
I know. There's still so much to explore. But don't worry, listeners. We'll be back next time with even more insights into the amazing world of computers. Until then, keep those CPUs cool and those transistors firing. So, I gotta say, after learning all this, I don't think I can look at a computer the same way again. It's like knowing there's this whole tiny universe humming away inside, making everything happen.
Oh, right? It really makes you appreciate the complexity hidden beneath the surface of these machines.
It's like next time my phone feels a little warm, I'll be like, those billions of transistors are hard at work in there.
That's the spirit. Or like when you see a loading icon spinning on your screen, just imagine those logic gates firing away, directing the flow of information, making sure everything happens in the right order.
Mind-blowing. It really is a testament to human ingenuity, isn't it? I mean, we took these incredibly simple concepts, electricity, switches, basic logic, and created machines that can do, well, practically anything.
It's really quite humbling when you think about it. And the crazy thing is we're still just scratching the surface of what's possible.
Like, who knows what amazing new computing technologies we might invent in the future.
It's an exciting time to be exploring the world of computers, that's for sure.
Absolutely. Well, I think that about wraps up our deep dive for today. We've covered a lot of ground, from those tiny transistors all the way up to complex logic gates and circuits.
We really have. And hopefully our listeners have a newfound appreciation for the amazing world of computing.
I know I do. So until next time, remember, keep those CPUs cool and those transistors firing.